Welcome to Fast Math Solutions with EJD. In this video, I'm considering this interesting question about the Euler's formula. We need to prove the Euler's formula, EI raised to power x equals cos x plus I sine x. Of course, that can be extended to something like E raised to power I theta equals cos theta plus I sine theta, or any other extensions you can give to this. So this is a very important thing in mathematics. And, if you check out my series on complex numbers, you see that this comes in prominently when we try to convert from rectangular form to polar form. When we try to convert complex numbers, right, from the rectangular coordinate system to the polar coordinate system. So this video provides a proof for this. So let's see how we can go about this. The first thing we need to do is to take note of the major components. The first component is e raised to power x, right? So in that case, we have e raised to power x, cos. Then the other component that is very important is cos x, and then lastly we have sine x. Now, and since the one key thing that combines all of them together is the idea of expressing them in polynomial form. If we need to express them in polynomial form, we have to talk about the Maclaurin series. We talk about the Maclaurin series, okay? And then we have to check the Maclaurin series for each of these key parts. So let's see how that goes. First of all, for e raised to power x, this is very popular. For the Maclaurin series for e raised to power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x raised to power 4 over 4 factorial and all that, That's the Maclaurin series for e raised to power x. Now, when you come to cos x, the Maclaurin series, remember cos x, when I also have a series, right, on basic calculus where I talked about functions, and at the point where I was talking about odd and even functions, we discovered that cos is an odd function, is an even function rather. So you see, 1 corresponds to 1x raised to power 0, and then minus x raised to power 2 over 2 factorial, even number, plus x raised to power 4 over 4 factorial, even number, minus x raised to power 6 over 6 factorial. Now you see 2, 4, 6, all even. So, and that is the Maclaurin series expansion for cos x. Now, when we come to sine x, remember sine x, we saw sine x to be an odd function, right? So, and for sine x, right, x is the same thing as x raised to power 1. And then you have minus x raised to power 3 over 3 factorial plus x raised to power 5 over 5 factorial minus x raised to power 7 over 7 factorial and all the rest. So it is important to take note of these things. So now that that is taken out of the way, let's see the next part. Look at what we have. If I squeeze, okay, if I do this, sorry, a bit of issue there. Okay, good. Now, if I actually do this, all right, so next we find e raised to power ix based on e raised to power x. We already know what e raised to power x is actually. So we know what e raised to power x is. So we can extend that to e raised to power ix. So since we already know that e raised to power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x over 4 factorial and so on and so forth, then we can do e raised to power ix, right? So wherever we see x, we put ix. So you have 1 plus, instead of x here, we have ix. Instead of x here, we have ix all squared. Anywhere you see x, just put ix. So we have, instead of x here, ix all the way. So what makes the difference will be the powers. So you have the powers. So here you have 1 plus ix plus I squared x squared over 2 factorial because I squared, right? So you have I cube x cube over 3 factorial, I4 x4 over 4 factorial, I5 x5 over 5 factorial, I6 x6 over 6 factorial, I7 x7 over 7 factorial, and so on and so forth. So what is left now is to take care of the i's. How do we deal with the i's, right? So of course, this is I here. There's nothing we can do to it. So we just bring it down. So I remains I. But for I squared, you remember, I itself is root minus 1, right? So it means that I squared will be root minus 1 squared, and root minus 1 squared is simply minus 1. And because of that, so we have minus 1 x squared over 2 factorial. So that's why we have this to be minus x squared over 2 factorial. Then, of course, I3 would be minus 1 times root minus 1. So that would simply be minus I. So that's why you have minus I here. For I cube, you have minus I, x cube over 3 factorial. Then the next one, you have I4. See, I4 is simply I squared times I squared. So that's I squared squared, if you like. And that is like minus 1 raised to power 4. That's minus 1 times minus 1, which is 1. Minus 1 times minus 1, that's 1 times minus 1. So all the way, it will just be 1. So that's why you just say I raised to power 4 is 1. Okay, I raised to power 4 is 1. So we have 1 times x raised to power 4 over 4. So we have this left now. So some 1 here, right? Then I raised to power 5, we start again. We start back from here. So I raised to power 5 is now like going back to normal I. Then I raised to power 6 is like going to I squared. That's minus there. Then I raised to power 7 is like the next thing after that, which is minus I for this. And then that's what we have. So the next thing you will discover is that from this expansion we have now, some of the parts, some of the components have I, some do not have. So let's see some parts. So I'll mark the part that have I in red. This one has I, this one has I, this one has I, and this one has I. So if we group all this together, see what happens. We have, for the part that don't have I now, we have 1 minus x squared over 2 factorial plus x raised to power 4 over 4 factorial minus x raised to power 6 over 6 factorial. And for the parts that have I, see what we have. Minus, so I just put the I outside because I is common. So we have x here. Then here you have x cubed over 3 factorial. That's minus x cubed over 3 factorial. And this one has I. That's plus x5 over 5 factorial. This one has I. So we have x7 over 7 factorial. Now you can already see from what we did the other time, this is looking like what we saw before. This is also looking like something we saw before. 1 minus x squared over 2 factorial and so on and so forth. So if we go back to where we are coming from, see, those ones without I are looking like 1 minus x squared over 2 factorial plus x raised to power 4 over 4 factorial and so on. And the ones with I are looking like sine x, x minus x cubed over 3 factorial. In short, they are actually all that. So we have seen a pattern. So this whole thing is looking like cos x, while this whole thing is looking like sine x. All right, sine x. So that's why we can say this whole expression is actually cos x, while this other part is sine x. So it is true that e raised to power ix equals cos x plus I plus sine x. So if you extend that to e raised to power I theta, that would mean that e raised to power I theta is also cos theta plus I sine theta. So if you have not subscribed to my channel, please do that. Hit the notification bell so you can get alerted whenever a new video is released. Thank you for listening. See you in the next video.